lecture on complex numbers. This is part one of a series of lectures. Just trying to explain to you what complex numbers are, and we are obviously going to manipulate these numbers as well as, of course, in the process have lots of fun. So you have a few pictures over here, a couple of animations. If you look at your top right corner, you're familiar with that. Is just a wave, passing through a double slit, and then you're just having a look at the consequence of that wave passing through a double slit. I wouldn't say a wave, but a pulse. And so you go back to Huygens principle and the superposition of waves. The picture on your top left, that's the wave function. You can see an IH bar there. So complex numbers or functions play a very important role in quantum physics, quantum mechanics. The bottom left is a circuit. But if you look very carefully at the circuit, it contains a capacitor, which is 100 microfarads. You have an inductor and obviously an EMF voltage supply there. And we're looking at obviously the voltage as a function of time with this oscillator circuit. So for instance, if you want to calculate, say, the impedance in the circuit or of that capacitor, then we would employ complex numbers. And then the last one is on the bottom right, and that is nothing more than your Mandelbrot diagrams from deterministic chaos theory or chaos theory. Very interesting that. So when you do have some time after your tests and exams, try to look up chaos theory as well as deterministic chaos theory. Fun, exciting stuff. And of course, we can't go by a single day not knowing what quantum physics is. So yeah, take a closer look there. But all of this, complex numbers, complex functions, play an important role for you, more importantly, your exams and tests. So let's get on with this lecture. Okay, look at that first equation, x squared minus 1 equal to 0. Not difficult to realize that x equal to plus or minus 1 will save the day. Pretty straightforward. The left-hand side is the difference of two squares, x minus 1 into x plus 1. And so that'll give us two solutions there, x equal to plus or minus 1. Substitute, and you can verify that. What about the second equation, x squared plus 1 equals to 0? Can we actually factorize x squared plus 1 equal to 0 with the knowledge we brought from school? The answer is no. Most people would go and say, okay, x squared equals to minus 1. And then you recall your teacher standing heavily over you saying, you cannot take the square root of a minus number, or you cannot take the square root of a negative number. Oh my goodness, yes, and it all stopped right there because we were looking for real roots. So x squared equal to minus 1, I'm now introduce you to the complex number, take you into a different plane altogether, and this is going to be very, very useful in engineering, in physics, you're studying fluid flow, as I said, electronics, electricity. So it's going to open up an entire new world to us. Amazing stuff. Introduced right at the very top, the square root of minus 1 for the first time. If you've not been sitting in my class, we're going to state that's equal to I. So the square root of minus 1 equals to I. So what does that mean? What does it mean? It means that this thing, I times I, is going to be minus 1. Okay, so you'll also see that the square root of minus 1 is j. This is a matter of notation. Some people call it I, some people call it j, whatever. Okay, so there we have it. So the square root of minus 1 in some textbooks would use j, or even lectures, and the other one will be square root of minus 1 is I. So same thing, equivalent. The algebra associated with these I and j are exactly the same. But for the purposes of this lecture, I would stick to I rather than j. So let's get on with it. Powers of I, okay, or powers of j. So we know that I squared would be I times I, and we know that is minus 1. What is I cubed? I cubed is I times I squared, which is I times minus 1, which is minus I. What is I to the power 4? Well, that is I squared times I squared, which is minus 1 times minus 1. That's a real number. That's going to give you plus 1. Now, just for you to think about this very carefully, what is I raised to the power 2019 equal to? And while we're having that much fun, I to the power 100 equal to that. What is I to the power 101 equal to? I want you to discover something about the powers of I or J. Okay, take a look at that, work it out, and if you're having problems, contact me. How? You can figure that out. Okay, we say rectangular form of a complex number. So we say the complex number can be represented by a real part and an imaginary part. The symbol we use for a complex number is the letter Z. So we can write any complex number in the form A plus, well, BI, so let's just stick with the notation here. B times I, where A is the real part of the complex number Z and B is the imaginary part. Now remember, when I speak of the imaginary part, it's not B times I, but the coefficient of I. If you're working in J with J, then it'll be the coefficient of J. So keep that very clear and in your mind. Okay, cool stuff, man. Right, just to cement the concept in your head, so the complex number can be written as a sum of real part and imaginary part. Just remember I squared is minus 1, so the root of minus 1 is I. If you just remember that, that's pretty cool. That's everything we've done up to this point, and we're going to move a bit further into the realm of complex numbers. Okay, folks, let's take a closer look at imaginary and real parts of a complex number. So I'm going to go Z equal to 2 minus, say, 3i. So the real part of Z, let's have a look at that. What is that equal to? The real part would be 2. Be careful here. What's the imaginary part? The imaginary part of Z is going to be minus 3, the coefficient of I. Just be careful of that. Right, so that is really cool. Now, I just want to quickly look at something here. These things are looking too simple for us, right? You know, so we are going to, let's see, let's try to define a number Z equal to 1 minus I, and we're going to multiply that by 2 plus, say I, like that. Okay. Now, when we multiply two complex numbers, this is just using the distributive law. So 1 times 2 is 2. 1 times I is going to be I. Minus I times 2 is going to be minus 2I. Now here, minus, why am I screaming? I don't know. I times I, so that'll be just I times I. That's how I like to write it. So this becomes 2I minus 2I is going to be I. Minus, what is I times I? It's minus 1. So that becomes 2, and there's a plus 1 becomes 3, and the final answer is minus I. Do you follow? Just do that again all by yourself before you look at my working out, confirm your answer, and then move on. Cool stuff. Okay, this is extremely important and useful. It's something called the conjugate. Now, you've come across the word conjugate in school. Conjugate acid-base pairs. Do you remember that? In the section of acid and base pairs, you looked at conjugate acid-base pairs, and you would remember, and you would have figured this out. It's called Governor's rule, by the way, that a conjugate acid-base pair differs by 1 hydrogen atom. Let me do that slowly. Governor's rule states that a conjugate acid-base pair differs by 1 hydrogen atom, H+. Think about what I'm saying. But anyway, it's got nothing to do with acids and bases. I'm just trying to go back in time almost 30 years ago when I was doing this sort of stuff in chemistry. But conjugate here for complex numbers, if you're given a complex number A plus BI, then its conjugate is A minus BI. If you've got a complex number A minus BI, then its conjugate is A plus BI. Notice the sign change applies to the imaginary bit only, not the real bit. Very, very important. Example, if I said Z is equal to 2 minus 3I, you tell me what is the conjugate. Z bar, that's what we write it as. Z bar is the conjugate. So let me just reinforce that as well. Notation is extremely important here. This is Z, its conjugate would be Z bar. If this is Z, then its conjugate is Z bar. So Z bar here would be 2 plus 3I. Do you agree? Easy peasy. want to show you something, and something that's extremely important, okay? So let's take a number, complex number, z equals to 2 minus I. Its complex conjugate would be what? What will be its complex conjugate? That's correct, it's 2 plus I. Now let's try to multiply the 2 out. Z times Z bar. What is that? Let's do this slowly. 2 minus I into 2 plus I. You look at this and say, oh, hang on, this looks like the difference of 2 squares. So the answer must be 4 minus I squared, which is minus 4 minus 1. No, just stop there. Let's do this slowly firstly. This is extremely important. Slow down, focus, put your phones away. So 2 times 2 is 4, then 2 times I is 2I, then minus that becomes minus 2I minus I times I. So that becomes 4. This cancels out. Minus into minus 1. What's the answer? Extremely good. Yes, z dot z bar is 5, and it's a real number. So when you multiply a complex number with its complex conjugate, you're going to end up with a real number. And think about this very carefully. There's another way of seeing this entire thing, and that is, if z is 2 minus I, then z bar is nothing more than, as we said, 2 minus I into 2 plus I. You square the first term, and not minus, plus. What's the coefficient of I? That's just that. So this will be 4 plus 1. And for sure, as God made little apples, yo-ho, 5. Think about that very carefully. So yes, it's a difference of 2 squares. But it turns out, because of I times I being minus 1, it becomes a sum of 2 squares. The sum of 2 squares. The sum of 2 squares. Find real and imaginary parts of this number. So I've got z equals to 1 minus j all over 2 plus 3j. Now, I don't know if you know why I'm going from I to j. Okay, let's just go back to I. So z is equal to 1 minus I all over 2 plus 3i, to confuse the hell out of you. So how do I write that? How do I find the real parts and the imaginary parts of z equal to 1 minus I over 2 plus 3i? What do we want to do? We want, let me write this down, we want to write z equals to a plus bi. If you got it in that form, then we know that a is the real part and b is the imaginary part. So take that number z equal to 1 minus I all over 2 plus 3i, and we'll do something fascinating with it. Well, you might say not fascinating, I'm going to say fascinating. I'm going to multiply top and bottom by the conjugate of the denominator. The denominator is 2 plus 3i, so I'm going to 2 minus 3i over 2 minus 3i. I've multiplied the entire thing by 1, so I haven't changed the problem. So in the numerator, I've got 1 minus I into 2 minus 3i. Now, walk with me. What's the denominator? What's the denominator? Complex number multiplied by its conjugate is going to be 2 squared plus 3 squared. Right? So let's multiply the top out. So you're going to get 2 minus 2i, and then you're going to get minus 3i, just exactly what you did in grade 6. That's minus and minus becomes a plus, but it's I times I, which is minus 1, so this becomes minus 3. Be careful, just check that. That is minus 3 and not plus 3. And the bottom is 9 and 4, which is 13. Let's simplify the top, collect terms. So what is 2 minus 3? Don't use a calculator. Those little monster machines are so distracting. Use your brain. So 2 minus 3 is minus 1. Minus 2i minus 3i is minus 5i all over 13. So if we got z being that, this is z, by the way. So tell me, what is the real part of z? The real part of this number here that we started off with, the real part, do you agree with me, is minus 1 over 13. And the imaginary part is what? Minus 5 over 13. Please, please, please do not move on until you verified this. Cool stuff, man. You just can't do one question and say, oh, I am a pro. If you look at these football players like Ronaldo, and I think there's someone called Messi, and I don't know the others, but these guys go out there and they practice for hours upon hours upon hours, and they've been doing it for decades. Now you're going to come along and say, okay, I've just done one problem and I'm an expert in complex numbers. No, you've got to do thousands of problems. You've got to eat them up, download stuff, ask your friend, WhatsApp, Instagram. Oh my goodness. Just go crazy. It's the only way you become good at stuff. So let's try and look at something else. So I've got this number z equal to 1 minus 2i all over 1 minus I plus 2 plus 3i all over, let's just try to trick you here, 1 plus I, right? Now we want the real and imaginary parts of this beast. So we have a look at that and say, okay, now we could take each of these terms, because there are two terms here. We can rationalize by multiplying the top and bottom by the complex conjugate, or what we can do is take a common denominator. Sweet, sweet, sweet. So it's 1 minus I into 1 plus I, and then you get 1. Now be careful here. 1 minus I goes there. 1 plus I term plus 2 plus 3i. That goes there into 1 minus I. Yo, let's start multiplying out. 1 times 1 is 1 minus 2i. I'm going to write this out slowly. Don't be a hero. Just do this minus 2i, and that's going to be plus I. Then the minus. Now watch that. Minus 2i times I. That's going to be plus 2. Please check that. Plus 2 times 1 is 2 plus 3i minus 2i. 3i minus 2i. 3 times I, it's going to be plus 3. Again, make sure you know that. And the denominator. Difference of 2 squares. No! It's the sum of those 2 squares. So it'll be 1 squared plus 1 squared. That would be 2. Please confirm that. Please, please confirm that. So let's look at the top. 1 plus 2 is 3, plus 2 is 5, plus 3 is 8. I'm going crazy here, man. Minus 2i and I is minus I. That's going to be 2i. And minus 2i cancels out. And what? And we get 8 over 2, which is 4. Please check this. Please check my algebra. Minus 2i minus I plus 3i. Yeah, the answer is 4. So this number z, has only got the real part, and the real part of z is 4, and the imaginary part will be 0. Awesome. So now we're going to be looking at a geometrical interpretation of complex numbers. So if you're given a complex number a plus say bi, sit over there, we can actually plot this in the complex plane, and these are known as Argand diagrams. Okay, so if you have a look very carefully here, the horizontal axis belongs to the real part. The vertical axis represents the imaginary part. So if you look at the function or the number a plus bi, so it'll be a units along the real axis, b units, positive b units along the imaginary axis, and we can draw this vector, which is that blue line with the arrow that represents the number a plus bi. Now, what is the length of that line? That's very, very important. The length of that line, which is the modulus of z, that's what we refer to it as, is going to be nothing more than a squared plus b squared, the square root of that. Okay, that's very, very important. So the length of the arrow is the root of a squared plus b squared. Notice the I does not feature in the magnitude or the length of that vector. So we now know exactly how to plot a number. Now, if you look very carefully, you'd also think, wow, associated with that blue vector, that arrow, is an angle. So relative to the zero axis or the real axis, we can call the angle theta. And that angle theta is called the argument of z. Say argument of z. And in math, we sort of write arg z is equal to theta. Now this is very, very important. So arg z equal to theta, but theta in radians, firstly, and that's confined to pi minus. Okay, so let's have a look here. So just remember that's the real axis there. This is really your imaginary. And let's look at the number z equal to 1 plus I. Okay, so 1 plus I, the real part of that number is 1. Okay, this is really bad. So scale, because the number of the vector would sit over there. 1, 1. Okay. And the magnitude of that number is very interesting. The magnitude of that number is really nothing more than 1 squared plus 1 squared. So the length of that little vector that I've drawn there is root 2. Okay. Now it's interesting to work out the angle associated with that. The angle associated with that vector is really going to be, I'm just going to use a different color that's going to stand out. That little angle, the blue angle there, we say tan of theta is the imaginary part of z divided by the real part of z, which turns out to be 1 over 1. So theta turns out to be pi by 4. So that angle, or the arc z, arg z is pi by 4 radians. Simple, right? Easy peasy. Cool stuff, man. Okay, just in terms of scale, so I'm just going to scale this up a bit. Let's go 4 minus 4 root 3i, like that. Okay, so we want to plot this number 4 minus 4 root 3i. Remember, here is just the real axis. This represents the imaginary axis. So we've got to go 4 units here in the real. So it's going to be 4 there. And then it's going to be minus 4 root 3. Minus 4 root 3. I don't know. It's somewhere down here. So we can have a look at that carefully and very quickly for yourself. Tell me where 4 root 3 is. I think root 3 is about 1.7 something. So minus 4 root 3 sitting somewhere down here. Go across, and then our vector actually sits down in the 4th quadrant over there. Now, recall that the argument of z lies between pi and minus pi. So if we had to take this angle, the outside angle, that's going to lie outside that range. So we cannot do that. But let's work out that angle firstly. So tan of theta is the imaginary part of z, right, neatly, all over the real part of z. And that's minus 4 root 3 all over 4, which is minus root 3. Now, root 3, let's have a look. If I remember from my special angles, let me draw this cute little triangle over here. And if I remember, that's 90 degrees. I always remember this 1, 2, because we know sine of pi by 6. There's pi by 6 here. Is 1 over 2, which is a half. This angle here is pi by 3, and the third side here would be root 3. So 1, 2, root 3. So you can see straight away that tan of pi by 3 is going to be root 3 upon 1. So it tells me that this angle here, watch this, that angle is minus pi by 3. Please check that. Okay, and minus pi by 3 lies within that domain, if you want to call it, not the range, minus pi by 3. So for this number, z equal to 4 minus 4 root 3, the argument z is minus pi by 3. That's something that's very, very important. Please check that out. So remember, we cannot take the outside angle, the bigger angle. Why can't we take the bigger angle, the one that I'm looking at right now? Because that angle lies outside of that range, the domain. So we're going to go use the negative angle, and it's minus pi by 3. What is the mod of that vector? What is the size? What's the length of that line? The length of the line, we write like this, is the root of 4 squared plus, and you got minus 4 root 3 all squared. That's 16, and then you got a 16 times 3, that's 48, and 16, that's 64. Is that right? So that's really nothing more than the root of 64, and we all know the square root of 64 is 8. It'll be a plus 8 because it's, think of it as length. Right, let's just double check. That's 4 squared. That's 4 squared. That's 16 times 3. That's 48. 48, and what did we have here? That's 4 squared. 48 and 16. That's 64. And the root of that is going to be 8. Beautiful. So we now know everything about that number. Z equal to 4 minus root 3i. Its magnitude is 64. Root of 64, which is 8. And the argument is minus pi by 3. Please, please make sure you understand why it's minus pi by 3 and not the angle of 300 degrees, if you want to call it, which is the outside angle, which is that blue angle that I showed you on that picture. Okay, cool stuff, man. Okay, let's look at another example. So take 1z equals to minus 8 plus 4i. Plot this vector on the Argand diagram. Again, there's your real part. There's your imaginary part. So it's minus 8, which is sitting there as the real part, now negative. Its imaginary part is plus 4, so it's up there. So you go all the way across, and you've got this vector. So you can draw it from the origin. Oops, should be a straight line, and it should be that vector over there. What is the length of that vector? So we'll refer to the modulus, which is really nothing more than minus 8 squared plus 4 squared. That's 64, is that right? Plus 16, which is root of 70. That's 80, whatever the units are. So you got root 80. Okay. Now, the angle that we're looking for, is nothing more than this chappy over here. Okay, so that angle, tan of theta, is the imaginary part over the real part. The imaginary part is 4. The real part is minus 8, so that's going to be minus a half. Well, minus a half, tan theta being minus a half, which quadrant is that? All right, so you basically work that out. We know that tan is going to be in the second quadrant. Obviously, it's there. And so theta is going to be arctan. There's a nice way of minus a half radians. And that gives me the angle straight away, which is in the second quadrant. And then if you remember, theta does lie between minus pi and pi. So that's really cool. Okay, so please take a look at that. Make sure you're working in radians, and yeah, so you should work out this angle quite straightforwardly. Please double check that. In this case, I'm not using any special angles. If you recall, if you go back to your work on trig, you see at tan theta equal to minus a half, you would have ignored the minus a half, the minus sign, introduced a reference angle, call it tan alpha equal to half, solve for alpha, and then say, okay, because theta is in the second quadrant, it'll be pi minus alpha. Just go back a bit to school. Instead of pi minus alpha in school, you would have said 180 degrees minus alpha, and that would have given you that blue angle that I'm indicating right now. Please check that. Cool stuff, man. Excellent. All right. So please just don't say, okay, now I understand. Only after 3 examples, I'm a master. Do a few more. Do a few more. Plot these things. First quadrant, second quadrant, third quadrant, fourth quadrant. I try them in different quadrants, work out the angles, work out the magnitude, and then you're good to go. So far, we've been looking at what we call the rectangular form of a complex number. We now want to look at what we call the polar form. Very, very useful. Now, think about this very carefully. In the r theta plane, if you're looking at that, so to speak, just say we had a complex number z equals to a plus bi. So a being positive and b being positive. Let's assuming that a was there and B was somewhere up there. So the number, we can plot that, and we have that. Associated with that vector is an angle theta. All right. The magnitude, oh sorry, the length of that thing is nothing more than a squared plus b squared, and arg z is going to be theta. Straightforward. Okay. Now, when you look at polar coordinates, you would recall something like this, that x is r cos theta, right, along the x, and then y is equal to r sine theta, where r is mod z, which is that guy. Okay, so the complex number z, if you look here, this is the real part, right? This is the real along the x. This is the imaginary part. So that number z can now be written as r cos theta plus r sine theta I. In other words, r into cos theta plus I sine theta. So that's an alternate form, which is the polar form of a complex number. You write the number as r into cos theta plus I sine theta. It's equivalent to the rectangular form. And once we've established the angle and the length of that vector, we can write it in polar form. So let's try and do a simple example, show you how we can write that in polar form. And once it's in polar form, then we can go back to rectangular form. So let's take that simple one, 1 plus I, right? That let's just go 1 plus I. It's a tiny little vector which sits there. It's a crazy vector there. We know that the length of that vector is root of 1 squared plus 1 squared, which is root 2, not 2. The angle tan of theta is the imaginary part of z over the real part. Write neatly 1 over 1. So theta is pi by 4. So where's pi by 4 in this picture? Pi by 4 is that little angle. You need a microscope to see that. So we can write z as the unit. So it'll be root 2, because remember it's r into cos of pi by 4 plus I sine of pi by 4. And if you know cos of pi by 4 is 1 over root 2, sine of pi by 4 is 1 over root 2, multiply that by root 2, and guess what? We get 1 plus I. Yay! So everything's in order. Pretty awesome. Cool stuff. Hey, you'll also note something very interesting when it talks about the polar form of a complex number, because we can write it as z r into cos theta plus I sine theta. Now this looks a bit complex. It's a bit clumsy. So what we do is we shorten that and we say r cos theta. You see, C for cos, I for the I, obviously complex, and S is sine theta. So Z is equal to r cos theta. You see the problem when people use J? You see the problem? R is equal to, what is that? The equivalent, right? I and J are equivalent. But cos theta, not to be confused with cos theta or cosh theta. All right, so please make a note of that. So for example, just to give you an idea, if I had to write something as z equal to root 2 cos of, say, pi by 4, what is that? That is root 2 into cos of pi by 4 plus I sine of pi by 4, and that is root 2 into 1. Please check that, plus I 1 over root 2, which is exactly the number we used in the previous slide, which is 1 plus I. So 1 plus I is root 2 cos of pi by 4. Follow? Please slow down if you don't. Pause, rewind, discuss, post on social media, whatever you can, just to understand it. Don't move on by just assuming things, because once you start assuming things, then you build a very shaky foundation. Shaky? unsteady foundation, and eventually that will lead to collapse. So make sure you understand the fundamentals before moving on. What have we done so far? We've introduced you to the rectangular form of a complex number. Then we introduced you to the polar form. You now exactly know how to plot a complex number on the Argand diagram to determine its argument angle theta. And there's also cos theta that we introduced, cos I sine theta. And we want even shorter hand notation. And so you'll see a lot of textbooks using something like r and theta, like that, the angle. Okay, very shorthand notation. So this is nothing more than, you can write it in this form if you want, and so it's cos theta plus I sine theta, like that. And then we're going to introduce you to the exponential form in lesson 2 of the complex number. So for example, let's just give you something like example, z equals to root 2. Let's go back to that. And the angle there was pi by 4. So we can write that as a root 2 cos of pi by 4. It's a very compact way of writing the complex number. So we know that is root 2, 1 over root 2 plus I 1 over root 2, and we get that number, which is 1 plus I as expected. So yeah, very, very important. You'll see that a lot in exams and tests, that very shorthand notation there. So the theta refers to the argument of z, and r is obviously the magnitude, or what we call the modulus of z. So remember, r is mod z, and the argument of z, as we said, was theta. And in this case, just to remember, theta lies between pi and minus pi. Awesome, guys. So hopefully this helps you as an introductory lecture to complex numbers. We're going to look at lecture 2. We're going to look at the exponential form, simplification, solution of equations, and of course, the expansion of things like cos n theta and sine n theta. We'll take you back to school and we'll derive for you those identities that you basically had to take a few lines, maybe half a page to derive. We'll do them all in 1 or 2 lines. Super duper stuff. Looking forward to showing you how to do that. So we'll see you on the other side of 10, whatever that means.